Hello, today we are going to talk about centroid Centroids and LCA algorithm. Okay, I remind you what is tree. Okay, and note, I'll find out what. Okay. Do you hear me now? I have problems with my microphone, but okay. Note, if G is 3, then the count of edges equals to the count of vertices minus 1. Obvious notes. Obvious to note, but we use the second one, that if we consider two vertices in our graph, for these vertices exists exactly one path between them. Okay. Before we consider definition of what is center, we must consider the following definition. Diameter. What is diameter of some graph? Diameter is maximum of length of all lengths between O and V. Length, I defined it like the sum of weights or just length, not length, dist. I think dist. I define dist like this. Okay, and how to find this diameter? Diameter of tree, for example, if we have, for example, some tree, diameter of this tree will be maximum walk, maximum pass. This is diameter, or this is diameter. Diameters can be the count of diameter. diameters can be not exactly one. There are many diameters can be in our graph. So how to find it? Choose some vertex over our graph, and let it be root launch from this vertex or DFS. And let for example, on this example, y is vertex with maximum depth. Okay, and just launch the FS from Y. And get that if that vertex with maximum depth then y z is diameter. No, okay. Z man can be here or here. It will be diameters too. So asymptoticity or complexity of this algorithm is ln, obviously, because we just launched 2DFS. And that's it. We can find several diameters. We need to prove that they are equal. We need to prove корректность. Как это на английском? Сейчас, how is it on English? Корректность. Вот second I смотрю. Корректность. Correctness. Так, что-то с микрофоном не то. Давайте let me turn off this microphone. This should be microphone. Алло. Так. Так. Ага. Все. Угу. Только меня теперь не слышно. Ой, надо было посмотреть. Okay. I think this this volume is normal. One second. Okay. 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 We need to prove correctness of, because there is many diameters in our graph. There are many. So consider that we know real diameter of the graph, and hence y z diameter 2 in our algorithm. Just check our algorithm. What it do. Consider our tree like this. This is diameter, real diameter of our tree. And notice that our tree look like this. Depth less than or equal than 1. This depth less will equal than 2, and so on. Symmetrical, like we get that this is kind of symmetrical graph, and what? And suppose we find our y in some subtree of this graph. We choose x vertex, for example, in this subtree, and notice that if our y not equal to a, it located in maximum depth on maximum depth in some subtree of left side of our graph, because if we consider y like in this in not in maximum depth, we get that this path is bigger than this, and we find a instead of y, so y located in maximum position. So we launch our DFS from y again, and we get that z located on another part of our graph in some subtree. Analogically, we find some z in some subtree, and analogically get that it defined on maximum depths. Okay, and we get that we find another walk in our graph, and notice that we get that maximum of dist AY and y and dist YP equals to dist AB. We choose maximum of them. If it's not true, we choose just another distance, maximum distance on our graph, maximum diameter in our graph. Okay, that's why these diameters can be we can get many diameters, and we can get that this diameter not equals to some diameter. Okay. Next is definition of center. What is center? We consider some algorithm and definition. If diameter of G is odd, is even, then we get that middle is center. Middle vertex is center. Okay. And if not так. And if otherwise middle two middle vertices are centers. Centers can be in our graph, the count of centers can be 2 maximum. Why is it true? I have some example. Example in this graph. Center will be here. And in this graph centers will be here and here. Okay, diameter here, or this is diameter, and we get that. Сейчас. Сейчас. мы видим, что диаметр лежит точно, диаметр, ну, на этих примерах диаметр точно 1, да, диаметр точно 2, и эта вершина, и эта вершина диаметра, и эта вершина, и эта вершина центра, всех диаметров. And we just need to prove that this diameter and this diameter can be equal for, this centers, the centers will be equal for all diameters. Note. Every diameter, every center the centers are the same for all diameters. Consider some graph. Consider some graph, and in this graph, suppose we have not exactly one center, not exactly. Second. We in this graph we consider that that length of diameter less than is odd, and suppose there are two diameters in this graph, and we get that it located in this part or this sub part. Suppose it in this part we get that if we consider center in this graph, and we get that Сейчас, 1 second. Suppose it look like not another diameter look not like this. It not go through this vertex. Suppose it look like this. We notice that this size, this length, less than this length, so this is not possible. So paths look like this, go through this vertex, and okay, and if it just 1 second, if it contains так. We can get that we find some paths look like this. So on it goes through, for example, this tree, step tree, and go through, and then it finds this vertex. This will be diameter 2, but centroid of this path will where is the centroid of this path? This okay, centroid of this path will be here because count of length in of this walk equal to count of this depth in this subtree. And why is it true? Because if you suppose that this path is less than this path, this will be not diameter, because we can find we can go through this to this vertex and get bigger path, and this will be diameter. So so if it greater, then we get bigger diameter. So that is противоречие, в общем. Okay. Analogically, if we consider diameter with real diameter with even length, we get analogically that center is center are centers for diameters are exact to vertices. Okay, a little bit confused, but let's consider next definition. Vertex V calls centroid. Centroid of graph G. Not graph, 3G. If G minus V, if in G minus V all connected components have size less than 2, or less than n divided by 2. Less or greater and divided by 2. Less or equal. So let's prove that Centroid always exists. Centroids always exist. And the size the count of Centroids, the count less than 2. Less or equal than 2. Okay. How to find Centroid? How to find Centroid algorithm? Okay, we perform some pre-processing for all vertices using DFS that count all of сейчас посчитать количество всех детей для всех вершин. That calculate all the count of children of all subtrees. How to do it? How do we do it? Find all subtree where this count of children. It's question for you. How to find this? Size count of children for all subtrees. If we consider some graph and we use the DFS on some, we choose root of tree, and how to calculate count of children for all subtrees if we launch the DFS. The DFS can be return to us count of children. So on exit of our recursion, we can calculate some sum. On input, if we check that if there is no children, that count is 1, and on exit, for example, for this vertex, we just sum all children's count of children's and get and plus 1 because we consider this vertex. So we perform pre-processing for all n and find Centroids. How? We consider some vertex and we Сейчас я посмотрю слово. 2 second. Ага. We descend or come down. We descend to vertex if sub 3 of this vertex U, for example, greater or equal than n divided by 2. And понятно that if we find 2 vertices with this condition, we get that our graph have n divided by 2 plus n divided by 2 plus 1 vertex, so it's greater there than n, so it's сейчас it contradiction. So this vertex is exactly 1, so we descend to this vertex and descend to vertices until we get that we can't descend in any vertex. No, can't descend in any vertex because its count is less than divided by 2. So this vertex will be centroid of our graph. Now, for example, if you consider this graph, and we launch the fs from this vertex. Ага. Так. We get that in this vertex count of the count of is 3, the count of children, and this vertex is 3, and this will be centroid. Окей. Что-то как-то тухло. But we get another situation. We get another situation that we can be this one centroid, there's 2 centroids. So how to calculate, how to find out algorithm that finds 2 centroids. If you look at this algorithm carefully, you notice that we can launch for the fs 2 times, or we can launch if we find some centroid, we just launch the fs from some children and gets the same thing, and children and this vertex have exactly 1 children in this case, but we just prove that we can find that we can find some centroid. So next will be why the count of centers less than or less or equal than 2. So I already proved that, by the way. of centroids less or equal than 2 because of this. If you consider let it be um, let it be two centroids that okay, do it again because we but use the same idea. The count of centroids. The count of centroids less or equal than 2. Okay. Consider our graph. Consider that we have 3 centroids. If we have 3 centroids, that if they connected, if all of them connected, we get a cycle, and we consider that we have 2 centroids that that means we have to consider that case that we have 2 centroids that not that isn't that doesn't connect with some edge. Let two centroids not let two centroids is not connected by edge. So we consider this case. There are two centroids, not centers. Centroids and centers is different. Let it be two centroids, and here is centroid 2. And let's find the count of children of the count of sub-tree in this graph, in this part. Okay, here's 2 divided by 2 and divide by 2 vertices here is, and divide by 2 vertices 2, and here's here greater or equal than 1 vertices. So we get that no, we get this. We get this. So we have 2 exactly centroids. And let's consider example that centroids and centers is not the same thing. If we consider some graph like this, some bamboo, веник, короче, вот, look, here we have centroids. Here we have centroids and centers. In this vertex. Блин, ну как помечать? Окей, this is easy. Что такое? And no, okay, a centroids centroid, B center, and AB is exact one vertex. So if we do stuff like this, we get that we get two centroids. Just 1, 2, 3, 1, 2, 3. We get two centroids here and here, and one center. If we continue to do it, we get exact one center and one centroid. So Venik, it's called Russian Venik. Venik is great example of difference between center and centroids. So next definition. Let G and H are graphs. We okay, and сейчас так, before we consider LCA algorithm, we need to consider isomorphism of graphs of trees, how to find it. So let G and H are graphs, then phi of V of G to V of H is isomorphism. If there is two conditions, phi is B action, I think it's called on English 2B actions. Just I check it. Bijection. And phi. Так. Phi keeps operations. What is this? We have one operation. Just connectivity of vertices. We keep that operation. What does this mean? If we have edge, if U and V is edge of G, then phi U, phi G, phi V is edge of, if S is edge of H. No, otherwise not edge. For example, what is this? We just the graphs are isomorphic if we can that renumerate some vertices of or our graph and get another graph. What is this? If we consider some graph, not exactly tree, it can be something like this, or and if we apply our isomorphism, we can just get another graph with another numeration. This graph is isomorphic. Okay. How to we can check in general case we can check fast graph are isomorphic or not, but for trees we can get that for polynomic time. How to do it? We just find a way how to correspond some tree to some number or some sequence. How to do it? Consider if we consider algorithm if there is exactly one vertex, we corresponded just null, and if but suppose we get but suppose we get bigger graph and we can launch the FS. We can launch the FS. Sorry. Let's consider mathematical induction. So we suppose we locate it in some point, and we know all the так, ну, where and x, y, z. So we have already calculated what is сейчас. We have already calculated номер класса эквивалентности, которому они принадлежат. we have already calculated class equivalency class that we created with our algorithm. We have already created this algorithm classes of equivalency, and we just renumerate it. We just know that for x, for y, for z, what is class equivalency for these vertices. And okay, and suppose we can say to store this to mark this class, this equivalence class, we just use map with vector int. In vector int we contain equivalence class for children. Так, ну как назвать? Сейчас. Ладно, просто m. Okay, and we contain when we in algorithm we just create vector based on these values, and sort it and push it to our map. And the second, and we contain some counter that calculates, that it iterates through all equivalency classes. A counter. In each iteration, we just add to this counter 1, and in this way we enumerate all the equivalency classes. So we correspond some tree. We correspond exactly one vector. Okay, let me explain using algorithm, because I have a feel that I didn't explain it good. Well, we consider our DFS and we just create vector for that we contain equivalency classes of children. Okay, and for all children, in our For all children, we calculate just equivalence classes. We already know equivalence classes for all children. That means we must to launch our defs before this, and then we push back to our equivalence class. What? No, we C2 C and when sorted, then we sort our equivalence class, our vector of equivalence class, and we check that if our map contains what? Egg? Not contains egg. We just we just have counter, some counter that we initialize as null, and we just enumerate all these equivalence classes. We consider mem vector and correspond to some new number. So that way we calculate, we correspond our vector to our sub-tree to sum 3. Ой, блин, сейчас. Сейчас. Second. Давайте на русском. С помощью этого алгоритма мы получаем, что мы каждому дереву, которое может перенумеровано как угодно быть как угодно, мы сопоставляем какое-то число. Вот, какое-то одно число. Как бы мы не нумеровали наше дерево, мы получаем вот тот же самый массив, потому что мы его сортируем, кстати. Вот. Ну, потому что мы все подмассивы сортируем. Вот теперь на английском. If we consider sum 3, we get that if we numerate it, we just get that if we sort for this array for all children, we get despite all our enumeration, we get the same isomorphism class. Okay, and this algorithm will works for all again, because this work for log n, and here's count of this is n, and we get n log n. Do you have questions? No, this is okay. I didn't hear you. Могу тебя слышать, ну хорошо. Так. Okay. So, how to... Now we to check isomorphism, we just launch this algorithm for two trees and get that. And if count will be equal in some root, we get нет, no. We that obviously that if we consider centroids and consider centers in our our graph, the centers and centroids in every tree, in every isomorphic tree, will be the same vertex, the same vertices. That means we just launch the FS from we just find centroids or centers for all n complexity, and we launch this algorithm twice. Not twice, 3 times for centroids, for centroid if we have two centroids. If we have two centroids of our tree, in our tree, we just launch this algorithm for this centroid, get some number, equivalence class, counter. Так. Just suppose it's woo, and we get some equivalence class for this woo, and we we just launch this algorithm twice for some centroid, and if we get that two centroids is equal, we just check it. This check and this check. If it performs, our algorithm we return true. So two trees is equivalent. So next is LCA. Think about time. We have enough time, but I will try to end it. Less common center. Ancestor. Okay. Consider tree. Consider some example. We consider root. Some root. And less common center for U and V in this tree will be this vertex think on example it's already, if you already understood what is LCA. Formally, it's the most the highest vertex on the wall, on the path from U to V. Okay, how to find it quickly? Approach. There are two approaches. The first approach is двоичный подъем. How it calls in English? How it calls in English? Let me consider. Двоичный подъем. Binary rise, binary lift. No, binary lift will be correctly. Binary lift. Binary lift. What is this? It's a very simple approach. Before we start, we just we launch the FS. Launch the FS from some vertex, get tin and T out race, and for this arrays we check is the center. We can check based on this arrays. We can check. And set store UV. We can check easily. What? How to check? By the way, you have in your test you have this. You have to prove this. In your first test, you just check that tin U less than tin V, and T out, and вот, давайте лучше так, and T out V less than T out U. Okay, so how to the algorithm, how to okay, now we do pre-processing. We create array lift. In this array we in this array we initialize with what? With root. Then we так, what is lift? Lift is if we consider this, we lift of lift of null u will be this vertex. Lift all 2u, 1u will be this vertex. Lift all 2u will be this vertex. It's a center in 2 to the power of k поколений. A center of u in 2 to the power of k. Сейчас поколение. Как будет поколение? Generation. Ну да, generation. Okay. So we initialize with root. By the way, maximum k will be maximum k is log n. I think you know why is it true. And we initialize this array with nulls, with roots. Then we how to do calculation pre-processing. Okay, lift. Then we calculate this. Lift of null u is parent of u. And we do the step. This is base, and we do step. How to do a step? Let we know lift k u for some k, and how to do a step. K plus 1 u. How to do a step? We consider our some walk, some paths in our graph that have 2 to the power of k plus 1 lengths. How to find it, how to find a center. We just find a center for 2 to the power of k. That means we consider this and do the separation again. We get a the answer. But why that works well? Because we initialize if we get that we already want to raise in in some in some center that doesn't exist in our tree, we get root. But no, we can do some functions that check that высота high. Сейчас мы можем завести просто какую-то функцию, которая проверяет, что у нас вот это вот k, оно меньше, чем log n, и все. Сейчас we can create some function that checks that this k less than log n. Ну, in this case we just return this, otherwise root. Oh, okay, and how to do step? We just call this function lift over okay лучше and how to do it. Okay, +1 u equals to what? Equals to lift of what? Of lift. Сейчас lift of lift. Yes, lift of lift. Of some u k and k. That's all you need to do. Okay. We can do this for all on log n. So for every vectors we can find a center that we just iterate. We just if we consider some vertex, we can iterate through log n, iterate from log n to 1, and just if we can lift to some root, if we can make lift, we just do it and again and again, and we just do. Мы делаем разложение этого пути на степени двойки. Вот как это так. We make we make split on. Блин. Сейчас секунду. We are doing decomposition of this pass on by 2 to the power of k's. So it's Okay, let me provide algorithm. Int LCA U and V if we consider if U is already at center of V, we just return U. Otherwise, we decompose our path for k is equals to log n. Сейчас log n вот так, да. Log n k greater than just minus k. We just do decomposition. If for center lift ku if it's a center, just if we consider our tree, no, if this is a center of our graph, we can make the step and перейти and skip this vertex. So we check this condition. We make the okay. I will end it and goodbye. So we check this and lift to this vertex if we can do it. And just if we do all this algorithm, we just return. Так. We return what? Lift null U sorry. It's strange. It's strange. Так, we return not it. Сейчас. Yes, of course, return null because we updated. Нет, no, we return just U. We updated this here and we return just U. So complexity will be like we have preprocessing and we have queries. Preprocessing will be performs for all n log n. And what? and query for O1. Нет, for O log n. But we can do it better. We can improve algorithm for O1 queries with sparse table. How can we implement it? No, okay, we consider approach 2. Approach 2, Euler walk. Euler walk, I think. Not exactly walk. Dot walk, those walk. We just consider our graph. Consider our graph and launch the FS in it. Somehow we rate it and just if we input to some vertex, we just print it. What I mean, every time we in the FS we input some vertex, 5, 4, 3, 4, 1, we just print it. 5, 2, 2, 2, 6, 2, 7, 8, 7, 9, yes, 7, 9, and that's all, I think. Just, and no, that's not all. 7, 2, 5. That's all. Okay, and in this graph we can notice that we, if we consider some sub-array, subsequence, of this sequence, if we need to find a center for 1 and 7, less common center, it will be in this segment, and okay, 1, 1, 2, 1, 5, 2, 6, 1, what? Just I missed something, I think. 1, 5, 4. Just 5, 4, 3, 4, 4, 1, 4, 5, 2. Okay, and here is it. Okay, and how to find it using sparse table? We just do sparse table on this on this segment, on this sequence, and what will be our function? Our function will be minimum. Our function will be minimum depth. It's just it. That's it. We just find in the sequence vertex with minimum depth, and it will be a center, less common center. Okay. To find LCA. LCA where we need to find vertex with minimum depths. Obviously, minimum depth is function with is idempotent, этот, как там, idempotent, associative, and what? Independent, associative, and what? I forgot. Where is for stable? Where is it? Ага. Commutative and associative independence. So we can build our sparse table on this function easily, and we just do this what I explained with on segment between U и V. Between U and V. So that's it. That's all. You have one piece task on this based on this algorithm LCA. You can implement this approach or this approach. It doesn't matter. But in this case, notice that queries will be performed for O1. So sparse table is very useful as a structure, by the way. Not we can use not not эти segment trees. We can use sparse table. So in some task. So that's all. Thank you. Bye.